Okay, thanks, Andy. Hopefully people can hear me. Yeah, and sorry again for the delay in getting set up. So I'm very excited to talk a little bit about Spark today, teach you a little bit on how to use it. Can you hear me? Is it? Okay. Hello. Oh, okay, this is better. Okay, sorry about that. So thanks, Andy. Sorry again for the delay in getting stuff set up. Let's get started talking about Spark. So I'll just jump right into it. So what is Spark? Spark is a fast and expressive cluster computing engine. It's designed to be a generalization of MapReduce, and at the same time, it's designed to be highly compatible with Apache Hadoop so that it's very easy to plug into existing Hadoop workloads. And it tries to improve over MapReduce in two ways: efficiency and usability. So to improve efficiency, Spark supports general graphs of operations that can be chained together into a job, not just the map and reduce you get in MapReduce. And it also supports in-memory storage, which is crucial if you want to do efficient data sharing between steps of your computation. And it turns out, in the real world, many computations are not just one map reduce job. They are actually many steps to do any kind of more complex analytics. And on these kinds of computations, Spark can run significantly faster. The second thing it improves is usability. So we wanted to make these jobs very easy to program. And to do this, we provide these rich, high-level APIs in Java, Scala, and Python. And we also provide an interactive shell, so you can use Spark from the command line to query large data sets. So what difference do these things make? So for the performance, Spark can run, depending on the application, we've seen it run up to 10 times faster than Hadoop MapReduce for on-disk data, and up to 100 times faster for in-memory data. It depends, of course, on the characteristics of your job. And in terms of usability, we've often seen users writing 2 to 5 times less code. Now, Spark started as a research project here almost 4 years ago in 2009, and it was first open sourced in 2010. Since that time, it's had an increasing sort of user and developer community, and today there are dozens of companies using Spark. Some of the big users are Intel, Yahoo, Adobe, and a number of startups and smaller companies around the world. The project's also an Apache project now. We entered the Apache incubator in June. Some really exciting stats I want to share about the project are about the community. So in the past couple of years especially, we've seen just quite a bit of growth in the community, and also quite a bit more people contributing to Spark and adding new features and improvements every day. So some of the latest statistics, we have over 1,000 members in the Bay Area Spark meetup. We have over 70 developers who've contributed code to Spark. Most of the developers are from outside UC Berkeley. Indeed, most of the code going into the project in the past few months has been from outside UC Berkeley. And we have over 20 companies that are contributing to the project. The cool thing about these statistics are, when I gave a similar talk at the AmpCamp last year, the number of meetup members was maybe about 300. The number of companies contributing was maybe 5 or 6. So the community is very quickly growing. And one final, interesting fact about Spark, if you look at distributed computing engines for big data, after Hadoop MapReduce, there have been a lot of new engines developed for different niches, things like Storm, Impala, Giraffe, and so on. Out of those engines, after Hadoop MapReduce, we're the one with the most active developer community. We have the most people contributing to the project, also the most patches going in. So in this talk, I'm going to start with a brief introduction to Spark. Just the goal of the talk is, not just to tell you why the project is exciting, but also to teach you enough that you'd be able to play with it and learn to use it. So I'll start with a quick introduction to it, and then a tour of the different types of operations available in it. This should be enough so that you can do some of the hands-on exercises later this afternoon and see how it works. Then I'll talk a bit about how Spark executes your job once you write it, and a little bit about writing standalone applications. I'll use PageRank as an example of that. So let's start with the introduction. So how do you write Spark jobs? So the key idea in Spark is that you write your programs in terms of transformations on distributed data sets. So you think about, OK, I'll make one data set. Maybe I'll run a map function on it, or I'll run a group by, or something like that. And I'll create new data sets as a result of that. And the objects you work with are called resilient distributed data sets, or RDDs. So these are just collections of objects spread across the nodes in your cluster. If you're using Spark in Python, they're Python objects. If you're using it in Java or Scala, they're just Java objects. You build them through these parallel transformations like map, filter, reduce, and so on. Spark has a wide array of these transformations. And Spark will also automatically rebuild them on failure. This is where the resilient aspect comes in. And finally, for each RDD, you get to control the storage strategy or the persistence for it. For example, you can say this data set will be shared among many jobs, so I want to keep it cached in memory. You know, this other data set, maybe it's expensive to compute, so I also want to replicate it across machines, and so on. So these are the objects you work with. Now, after you create your RDDs, there are two types of operations you do on them, transformations and actions. So transformations build a new RDD from a previous one, and examples of these are things like map and filter, and these are all lazy operations. Basically, they're not evaluated right away. Instead, Spark waits to see all your transformations and then comes up with an efficient execution plan. Actions, the things like count or save or collect that take an RDD and output a result, either bringing it back to your program or writing it to the external world. So these are things that sort of trigger the computation and cause the lazy stuff before to be evaluated. So I'll just show how these things fit together in a simple example. And this one will be mining some console logs. And basically, we have some files with error messages in them across a Hadoop cluster. We want to load just the error messages into memory and then ask for, search for different patterns in them. And I'm going to show this example in Python. This is actually code you can type into our Python shell and just run on a cluster. So this is our cluster here. We have a driver node, the master, and then a bunch of workers. And this is the code we'll type in. So first thing we'll do is create an RDD called lines, which is a text file in the Hadoop file system, HDFS. You can just read directly from HDFS. And this is going to be our base data set, and it's going to be a collection of strings, one for each line in the log file. Next, we're going to do a transformation. So we're going to filter out the lines that start with error. So now the parameter to that, if you're not super familiar with Python, this lambda is a way of specifying a Python function in line. So to filter, you can give it any Python function you want. You can just write a function above, in your program and pass it in there. And if you want, you can write it in line with a lambda. So lambda means, it's a function with one argument s, and for each string s, return true if it starts with error. So we're just filtering out those error messages. So this gives us back a transformed RDD. Next, maybe we want to do more operations. So here I'm going to do a map. Maybe these are tab-separated fields, and I want to split each string by tabs and pull out field number 2, which is the actual error message. And finally, I can choose to cache some of the data sets, and I'm going to cache only the messages in memory. I don't want to load the whole file. I just want to keep these because these are the ones I'll be asking queries about. OK, so at this point, nothing's actually run on the cluster. All these things are happening lazily, so Spark just remembers that these are the operations you want to do, and it waits until you run an action to actually execute them. So let's do that next. So the next thing we're going to do is we're going to count how many of these error messages contain foo. This is how you search if string contains another string in Python. And so count now is an action. Count has to return back a number. It's how many elements are in this data set. And so the system has to go and run something on the cluster. So when this happens, Spark looks at the operations in your job, and it comes up with a plan to execute it. So what it's going to do here is it's going to see, OK, we're starting with a text file. Let's see where the blocks of that file are laid out across the cluster. Maybe each machine has a different block. And then it's going to send tasks to each machine to execute them. Those tasks are going to do first the filter and then the map, and they're going to process the block, send back some results. And in addition, each node is also going to save in its own memory the partitions of the cache data sets that it's built along the way. So now each node has some of these filtered error messages in memory. OK. Now, next time you run a query on this data set, maybe foo wasn't the problem in your logs. You're going to search for bar. So let's search for that. Now we're going to send tasks to the nodes based on the memory placement of the data. And we're going to read the data directly out of memory without processing the file again and send back some results. And of course, you can do more than just filter and count in Spark. You get a whole array of operations. So just to give you an idea of the difference this makes and how interactive it is, one of the sort of tests we do is a full text search of Wikipedia on 20 machines. Wikipedia is not that huge. It's about 60 gigabytes, but it's still something that if you're working with the data from disk and certainly on a single machine, it takes a long time to go through it. So if you do this with on-disk data on a cluster or with Hadoop, it takes about 20 seconds to do a full text search. If you do it with Spark within memory data, it takes about half a second. So you can really take fairly large data sets and work with them interactively, same way you would from the Python shell. And this also scales up to much bigger data sets. So another test we did is 1 terabyte of data on 100 nodes. And there, again, just doing brute force, plain text search, you can do it in about 5 seconds, whereas scanning the whole thing from disk would take about 3 minutes. So the other thing I want to mention with RDDs that is cool about the model is how it provides fault recovery. So all the data sets you build out of these transformations, remember their lineage, which is the series of transformations you used to build them. And they can use this to efficiently recompute data if one of your nodes crashes and you lose that out of the cache. So in this example, we had a text file, we did a filter, and then we did a map. Spark is going to remember this chain of operations. So it's going to know, it's going to know, okay, you did a filter with this function, contains, and you did a map with the function where you're going to split it. So that's how it's going to remember. And then when you go back here, if we ever lose one of these nodes, for example, I guess you can't see my mouse. Okay. For example, say that we lose the cache on node 3 over here. Spark is going to apply just the filter and map on just this block of the file and build it back. Okay. And final thing, lots of people ask, okay, keeping data in memory is great. What happens if it doesn't fit in memory? And so Spark is designed to degrade gracefully in that case. So it can operate well even if only half your data fits in memory or a quarter or whatever else. What it will do there is it will keep some of the data in memory. For the rest, it will put it on disk. And you'll get performance that's somewhere in between having the whole thing in memory versus the whole thing on disk. So this is just a graph showing, in a cluster, if we disable the cache versus we allow different percents of the data to be in memory, we get this nice sort of change in performance. Okay, so that's a really quick sort of overview of what you do. And the rest of the talk, I'm going to jump into quite a bit more details. The final thing I want to mention is the APIs are not just in Python, but also in Scala and Java. So Scala, if you're not familiar with it, it's a higher level language for the Java VM. It compiles to Java bytecode. It interoperates very cleanly with Java. And it's also fast because it's statically typed, but it has this much nicer syntax. And so some of the things you can see, this is our Scala example here. So one of the cool things about Scala is you don't need to specify types everywhere. It infers the type if you just have a variable and you don't declare its type. And the other thing is it supports these inline functions, kind of like the Lambda expressions in Python. But this, it's just running on the Java VM. And if you want to use Spark in Java, we have an API in Java as well. Java doesn't yet have function expressions, but you can still create functions using basically an inner class. And it's still, we've tried to make it as concise as possible. Okay, so one of the questions you'll have, given these options are which language should I use? And in the hands-on exercises here, we've designed them so you can actually do the Spark exercises in any of these languages. So standalone Spark jobs can be written in any of them, but the interactive shell, which is one of the things I'll show a bunch of, is only available in Python and Scala because Java doesn't have an interactive shell. So if you're a Python user, you can safely use Python for both of these things, and it's going to be fine. If you're a Java user, I recommend learning just a little bit of Scala for the shell. We actually have resources in the exercises to do that, and it's a really fun language, and using the shell is one of the best ways to actually play with data and to learn Spark. And in terms of performance, Java and Scala are also going to be faster due to the static typing, but Python actually often does fine. I mean, I've seen certainly Python with in-memory data on Spark can go quite a bit faster than Java with on-disk data and Hadoop. So it's still a good option. Okay. So in my talk, I'm going to do something slightly weird because I want to showcase both of the APIs. I'm going to have all the slides be in Python, but I'll be typing in some code that will be in Scala. So I want to present you just a very short cheat sheet so you can see what it looks like. And hopefully it will be pretty self-evident when I actually type in some code. But this is Scala syntax in one slide. So let's see, there are a few things going on. So first is the stuff about variables. So when you declare a variable, you say var, you give it a name, and you can optionally give it a type. So :int means it's going to be an integer, and you can give it a value. If you don't give it a type, Scala will actually infer the type based on what you're initializing it to. So this doesn't save too much typing when it's int, but when it's a more complicated type, this can make your code quite a bit smaller. And finally, you'll sometimes see instead of var, you'll see val. Val is a constant. It's like a final variable. And Scala actually being a language that supports functional programming, it actually really encourages using immutable variables just to make code easier to understand. So this is just a read-only. To define functions, this is how you define a function. You basically say def, you give it a name, you give it arguments and a return type. And if you want, if your function is just one expression in Scala, you can just put the expression you're going to return right there. No need for a body and a return statement and all that. If you give it a body, instead, you can write a bunch of statements in these curly braces, and then the last statement is the value returned. Or if you want, you can use a return statement. Okay. Now, the other thing is the functional expressions. So Scala's collections library support a lot of the same operations that you'll see in Spark, like map and filter and reduce. They're actually a good way to learn these. So I'm just showing a couple of these here. So in this one, I'm making an array of numbers, and I'm going to do some maps. And these are different ways of writing the same map function. So you can write the function fully with types. You can say, OK, well, it's going to take an int, and it's going to return x plus 2. I'm just trying to add 2 to every element of the array. You can omit the types, and the compiler is going to figure out what they are from the context. And if you want, there's this super shorthand syntax where if you use an argument only once, you can just give it the name underscore, and that's just going to plug that one in there, and you don't need to do this whole x arrow x business. Okay, and if you have a function with 2 arguments, you can pass the arguments, give them name, or you can use each one once, and you get this kind of funny-looking syntax with 2 underscores. Last thing I want to mention is all the classes and stuff you'll be doing are also Java classes, and any Java class you have, you can easily create it in Scala. So that's just a quick overview. So you can find a lot more details about this online. We'll have some resources as well. Okay. So let's jump into a few more details about what operations you can do with Spark. And for these operations, I'm also going to show them to you live happening on a cluster. So the easiest way to learn Spark is using the interactive shell. And if you download Spark, you can just launch that as Spark shell for a Scala one or PySpark for a Python one. And these are special versions of the Scala and Python interpreter that we modified slightly in order to be able to ship code to a cluster so you can run on a distributed system. The shell just runs on your machine on one thread by default, but you can easily connect it to a cluster as well. And the way you do that is with the master environment variable. So you can pass local as the master to run it locally. You can pass local with a number of threads to use multiple cores on your machine. Or you can give it the Spark URL to connect to a Spark cluster, or a Mesos URL to connect to a Mesos cluster, and so on. OK. And I'm just going to show you that a little bit in action using this shell that I have on EC2. So I'm just going to log into this node. Hopefully it works. Let's see. OK, so what I have here is I've launched a 20-node Spark cluster on Amazon. I just used some scripts that come with Spark to launch it. And on this cluster, I've actually put in that 60 gigabyte Wikipedia data set I was talking about. So we'll be playing with that from Spark. But before we do that, we have to actually, we logged into the machine, and I'm going to go into screen just in case we disconnect, and we have to actually launch the Spark shell. So if you just do Spark shell like this is going to launch it locally on just the master machine. It's not super exciting, but you can work with it that way. So this is just running locally. If you want to launch it on the cluster, you can pass this environment variable, and there's this file on there that has the cluster URL, and we can launch it on the cluster as well. And so it takes a little bit of time to load, but it will come up soon enough. Okay, and then this is it got a bunch of nodes, and then these are nodes registering, telling it how much storage it has. So if we look at the cluster now, you'll see in here there's one running application, which is the Spark shell. Okay, so let's start to use this to do some stuff. So first of all, this is just a Scala shell. You can type in expressions, get them evaluated. You can do all the stuff I showed before to declare variables. All that stuff works. But in the Spark shell, you also get this special object called Spark context that lets you actually use the distributed features. And that object is available as a variable called SC. Okay? And in the Spark shell is just created for you. Okay. So one of the first things you'll want to do with the Spark context is create some RDDs. And there are several ways to do it. So one way is if you have just a local collection, you can easily turn it into an RDD using Spark context.parallelize. So this is really great for just playing around with it, without even a cluster, just in local mode. So in Python, you'd give it a Python array. And here, I could do like this. Sorry. Okay. And now we get an RDD containing integers. Okay. Alternatively, you can make an RDD that represents a file in your cluster, and you can use Spark context.text file if it's just lines of text, or if you have an arbitrary sort of Hadoop data format, you can use Spark context.Hadoop file. So Hadoop has this plugin class called input format that lets you connect to different storage systems, and Spark uses the same interface. So it can talk to any storage system that has a Hadoop plugin. This is currently only in Java and Scala, but we're going to add it to Python soon as well. Okay, so that's how this works. Let's see. Okay, so in this case, I'm going to make a data set that's actually our text file, our distributed text file. And this is sitting on the HDFS cluster. And so this is going to be an RDD of strings that's sitting over there. OK? All right. So what do you do once you've created the RDDs? So next, you get a whole bunch of transformations you can do on them. Let me just go through these in a little more detail. And then we're going to go back and actually do them on Wikipedia. First transformation you've already seen is map. Map, you give it a function. It just applies it to each element in the data set. So you had 1, 2, 3. Maybe you want to square each element, and you get 1, 4, 9. OK? Next, filter, you've seen it as well. You give it a function that takes an element and returns a Boolean. And we're going to keep only those elements that pass the filter. So here we're going to filter out only the even numbers. So this is the squares, and only 4 is actually an even number. And finally, another one you'll see is called flat map. This is kind of a funny name, but that's just what it's called in functional languages. So this is where you map each element to a list of other elements, and then you just you stick all those lists together to form a new data set. So for example, in Python, if we had this data set 1, 2, 3, we can map each x to range x, which is the numbers from 0 up to x minus 1. So this is, like the range 3 is 0, 1, and 2. And this allows you to produce multiple output elements for each input. One good place to use this is, say, you have a bunch of text and you want to split it into words or things like that. But so you can do that as well. OK. Once you do the transformations, you've built some data sets, you also get a whole bunch of actions. So collect is the opposite of parallelize. It takes an RDD and brings it back to you as an array, like a Python array or a Java array. So you'll often do this, say you do a big filter and then you want to see which elements pass the filter. Take gives you back just the first few elements of the data set. It's great for peeking into a data set to make sure all your transformations have worked correctly. Count tells you the total number of elements. Reduce lets you add them up using a function. So for example, you want to add up all the elements. You could give it a function that knows how to merge 2 of them, and it's going to apply that to merge everything else together. And finally, save. There are different versions of save that let you output data to a storage system. OK. So I'm just going to show that stuff happening with Wikipedia here, just so we get a sense of how it works. So first thing I'm going to do, I'm actually going to use another simple action, which is first. It's just returning the first element of a data set. And so I'm going to do that to peek at the first line of text in the file. So when you do that, Spark actually notices, wait a minute, I only need to read 1 line. So it just computes it locally on your machine. And you just get that first line, and you can see what your data looks like. So this data we have here is a tab-separated values file of Wikipedia. This is the first line of text in the file. And basically, each line has 5 fields on it. It has an article ID. It has a title. It has a date when it was last modified. It has an XML version of the article with lots of angle brackets and slashes and stuff. And then you don't see it, but there's a 5th field, which is a plain text version of the article as well. So one of the things we may want to do now is pull out only one of these fields. Maybe we only care about analyzing the plain text. So for example, we can do like this. So we're going to map each file. We're going to split it. So sorry, I'm going to write this the full way. So we have a line of text. We're going to split the line by tabs. And then we're going to pull out the last element of the array. So this is going to give us just the plain text. OK? And then if we do text.first, it's going to, again, compute only the first one for us. And we see this is the plain text. So and yet, which was our first article, is some kind of album that had an alphabetically very early on title. So it was the first article in Wikipedia. OK. If you want, you can also try other things like, let's say we want to take 3 of the text. So now we got an array of guys. We got first there's and yet. Then we get this amorte e carnevale. And then we get this aim, which is a settlement. So you can easily peek at just some of your data in this way. OK. So let's try to also do a distributed operation on this. So first I'm going to tell Spark to cache these guys in memory after it computes them, because we're going to ask a bunch of questions on them. And then let's also try a distributed operation. And I'm going to filter for each. Let's count, for example, how many of the texts contain Berkeley, and count that. OK. So now when we do this, we're not asking for just the first one anymore. We're asking for the count. And it's going to launch tasks across the cluster. So it takes a little bit of time to do this the first time. But basically, it's sending that function we wrote to a whole bunch of the nodes to actually run this. And it goes along. And eventually, it will give us back an answer. And so we got, OK, so in total, we had 16,000 articles that contain Berkeley. Now, the other cool thing is, like, now this data is loaded in memory on the nodes, so we can ask further questions, and we can make it happen quite a bit faster. So we had 16,000 articles that contain Berkeley. Let's try doing, for example, Stanford, and see how many it has. And when we do that, it's only 14,000. Yeah, and we got that answer. So yeah, okay. And if you want, we can go back. We can do this one again. It's still 16,000. It's still good. So it's not like we only cache some of the data. Okay. And finally, we can do a few other things. So for example, let's take, for example, for each guy, let's take the first word of each article and just bring it back to see what the article is about. So this, I'm going to just take the first word of each one. I don't want to collect all of them because it's a lot of articles, and bring it back. And now we get an array about different things that these articles were about. Maybe splitting maybe taking the first one was not not super exciting, but yeah. So this is the first article is the 2009 California something. The second one is AFI, a fire. Then there's an academic quarter and all this kind of stuff. So you can peek at just the first few words and see what these articles are about. Okay, cool. Okay, so this is kind of some basic stuff. This is enough to start exploring some data. And the only other thing I wanted to cover is how to do some of the more complex operations in Spark. And a lot of these operations involve key value pairs. So with many data sets, once you work with each data item locally for a while, you want to regroup them again in some form. For example, group them by ID or sort them or something like that. And in Spark, you can do these kind of transformations by creating key value pairs. So all these languages support key value pairs. In Python, they're just a built-in thing. You create a pair of AB just by putting it in parentheses, and you can access each element of it with the index 0 or 1. In Scala, you get very similar syntax to Python, but they're called _1 and _2. And in Java, you can create this class called tuple2 that represents a pair, and you can, again, access the fields with _1 and _2. So let's see what you can do with these guys. So once you have an RDD with key value pairs, you can do these new operations that happen by key. So here we have maybe information about pets that different people own. Someone owns 1 cat, someone owns 1 dog, and maybe someone else owns 2 cats. One of the things you might want to ask is, okay, for each type of pet, how many are there in total? So we could do that using reduce by key. And that's going to take, for cat, it's going to take the values for cat and add them up. So we'll get 3. And for dog, there's only 1, so we'll get 1. So this is kind of like the reduce and map reduce. It's a way to do a distributed reduce. If you don't want to just aggregate the values, you can also do group by key. That gives you instead an array of elements for each key. So you get to see all of them and look at them, maybe do something with them. And you can also do sorting by key. So that just changes the order of elements in the RDD. And then if you take the first or the first 10 or whatever, this is how you do a top 10. And if you're familiar with MapReduce, there's something called a combiner in that. So reduce by key also implements the equivalent of a combiner. A combiner is if you have an associative operation, we're going to aggregate the data locally on each machine before merging all the results. Okay. So using this key value pair stuff, now you can do sort of the hello world of MapReduce in Spark as well, and that is word count. So word count, the way it works is you have a text document, say a bunch of lines of text, and you want to know how many times each word happens in there, and this is how you would do it. So you'd say, okay, we have a text file. We're going to do flat map, so we're going to split each line of text into words. So one input record becomes multiple output records. And now we just have a bunch of words. We're going to map each word to this pair of word, comma, 1, and then we're going to add them together with reduce by key. We're going to add up all the ones and get the count. So that's all it is. And this is kind of, this is how it executes. So basically, we start with input records that have different words. we map them, the flat map splits them up into one element per word. The second map here turns them into key value pairs, and then the reduce makes us add up together the values for each key. So we get, okay, this one happened twice, this one happened once. Okay, so that's how that looks. And finally, you get the key value operations are also how you do joins and co-groups between data sets. So if you're familiar with SQL, these are some common operations you do. So say you have two data sets about web pages. Maybe the first data set is about visits, and it has key value pairs where the key is a page someone visited, and the value is the IP address. So, this one person visited index.html, someone else visited about, someone else visited index. And then say you have a second data set, which is the page names. So for each key, what is the name of the page? This is often how you organize, data sets. You're going to have different tables with the same key. So one of the operations you can do is join. This is for each key, give me all pairs of one element from this and one element from this. So this is when you want to see the page name and the visit together into one record. So what happens here, okay, for the first guy, index.html and 1, 2, 3, 4, we give you 1, 2, 3, 4 and also the page name, which is home. For the second guy, index.html and 1, 3, 3, 1, we give you home again. And for this one, we give you about. So this just gives you all these pairs. If you want to do not get the pairs separately, but just get all the values, you can use co-group. This is, again, if you're familiar with Pig or SQL, there are similar operations there. And this one gives you an array for each key. It gives you all the values from the first data set and from the second. So that's basically how you do these things in Spark. And the final thing I want to mention is setting the level of parallelism. So basically all of these pair RDD operations let you control the level of parallelism, the number of tasks they run on, and you can do that as an optional second parameter. So for example, if you say, I'm going to reduce by key, and I think I have lots of keys, so I want you to do it on 5 different nodes, you would pass in a 5 over there. Same thing with group by key and join, you can tell it how many to use. If you don't specify the level of parallelism, Spark will try to infer it automatically based on how big the previous data set is. Okay. So the final thing I want to mention about actually using this is how the functions you pass to Spark interact with the rest of your program. So you saw, I was typing in a bunch of functions. They got sent to all the nodes. But what happens if they're using other stuff from the program? So essentially what happens is all the variables you use in one of these closures will automatically be sent to the cluster for you. We analyze which variables your code uses in both Scala and Python, and we just send those along with the task. So for example, if you wanted, instead of me typing in Berkeley, you wanted to get the query from the command line and then search how many lines contain it, you just create a variable and use that in your function. There are, however, some things to be aware of. So one is that each task gets a new copy of the variable. If you update the variable in the task, we're not going to magically send it back and synchronize it with the program. It would be really expensive to do that. So basically, you can think of these as becoming read-only once you've used them inside a closure. Because the variables are sent across the network, they also need to be serializable for Java or pickleable for Python. Most of the built-in types you deal with are, but if you make a custom class, you'll have to make sure it supports being sent across the network. And finally, one tricky thing people run into sometimes is you write some Spark code inside an object, and then you use some fields of the objects. And that is not completely obvious, but that actually will send the whole object, because that's what accessing those fields means. So just as an example of that, this is a Scala one, but similar things can happen with Python also. So if you have your object, it has a parameter that's a field, but it also has other stuff like a log file that it's opened as its fields. and you use param in a map, this is actually not going to work. The reason why is when you're accessing param here, it really means this.param. So it means you're accessing the current object and asking it for its field called param. So we have to send all of that object across. And you'll get this exception which says, well, my RDD app object is not serializable. And that's because it has this log thing that isn't serializable. So there is one really simple way to avoid that, which is if you're going to use fields above, always create a local variable that's a copy of the field. And as soon as you do this, the meaning of it is very clear. The compiler doesn't try to access it using this. It just accesses it using the local variable. So now this is actually going to work fine. So I just want to mention this because it's like the one thing that can sort of trip people up. But that's how it works, and it's a pretty cool sort of feature to have. So if we go back to our example, we could do stuff like this. You could declare a variable, that's our query, and we could do. Sorry, let me go farther up. We could do stuff like this, and actually just launch that and hopefully get something back. Oh, let's see. I think there's something happening with the connection to this guy here. Okay, yeah, well, okay, I don't know what happened there, but it did finally finish. Okay, so yeah. Okay, cool. All right, so that's what it is. So there are lots more Spark operators you can look at. So you can find a bunch of them in the documentation online, and I'm not going to have time to go into it, but definitely check it out. We tried to make most of the common things you want to do with data already available as a built-in operator. Okay, so let me talk briefly about how jobs execute and then how to write standalone apps. Okay, so when you run Spark, Spark itself is just a library in your program, and every program you have, every Spark context you create is a separate instance of Spark that's going to get its own separate workers on the cluster. One thing you'll notice here is Spark doesn't have like a single master that all the jobs go through. Instead, each application completely owns its own workers, and if one of your applications failed, it doesn't cause the other applications to die. So that's how you link to it. Now, the Spark context object can connect either to, it can connect it can either create threads in your program to launch the task locally, or it can connect to a cluster manager. So for the cluster managers, we support Mesos, we support Yarn, and we also have our own very simple standalone mode, so you can launch Spark without having to install anything else. And the workers themselves access data through Hadoop's input format API. So you can read not just from HDFS, but also HBase, Amazon S3, Cassandra, all these different systems that support a plugin for Hadoop. Now, when you give Spark some operations to run, inside it has this scheduler that tries to do a bunch of optimizations for you. So it looks at the graph of all the dependencies between your data sets. You can have both simple dependencies like this map and then filter, and more complex ones where two data sets are being joined together to create another one. And it supports optimizing across this whole thing. And the scheduler also automatically pipelines your functions together to make them more efficient. So for example, in this case, we're doing a map followed by a filter, and Spark is going to group these together into essentially one map function that does both the operations incrementally on each record as it comes in. And it's going to execute that together to make it efficient. The scheduler is aware of data locality. It knows which data is in memory, and it knows about locality for HDFS, so it can schedule tasks close to the disks that have the data as well. And the scheduler is also aware of data partitioning, and that can often help you avoid shuffle operations across the network. So one example of this is here we're doing this join. So we have one data set that we grouped by key, and then we're going to join it with another using the same key. Now, when you do a distributed join, usually the way to do it is you hash each element, and you take the hash code, in this case, mod 3, to send it to a machine, and you group the elements by key that way. But in this case, we know that this data set was already hashed by key because we did the group by before. So Spark knows it doesn't have to shuffle it across the network again. It just takes all the things in partition 1 and sends them directly to whoever is going to deal with, with the things that hashed it out over here. So this is one of the things that can save time. Okay. And finally, the scheduler supports a few more advanced features that I just want to mention in case you want to look into them. So this partitioning across nodes is actually customizable. If you have a data set, like say of web pages, you can choose to partition them by domain name, for example. That can make it quite a bit faster. The storage is also customizable. I just cached data in memory as, I just called cache, but you can also tell it what format to cache it in and whether to replicate it to nodes. You can even cache data on disk if you want. There are also some special things called shared variables that let you express common data sharing patterns like broadcast or like counters or accumulators where everyone wants to keep incrementing a counter. And you can find out about all these things in the docs. All right. And so that's hopefully a bit of a taste of what the actual system will do. So that's that. So final thing I want to talk about is how you would use this in standalone applications. I've shown it in the console. So it's actually fairly easy to link it into standalone applications because it's just a library. So if you have a Java or Scala project, you can add a Maven dependency on Spark using Ant or Maven or your favorite build tool. And this is sort of the group ID and artifact you have to put in. If you have Python, you just run your Python program with our special script called PySpark, which is going to set up, connect it to the Java side of things and make sure everything is accessible to it. And pretty much the only difference between console usage and standalone apps is that you have to create your own Spark context and you pass in some initialization code. So here's how you do that. So I'm going to show it in all 3 languages. So basically, when you create a Spark context, you pass it 4 different parameters. You pass it a URL for your cluster. This can be local to run locally, or it can be a distributed cluster, like I showed on EC2. You pass it a name for your job. You pass it the path where Spark is installed on the cluster, so it needs to know that to launch processes on those nodes. And finally, you can pass it a list of jar files for your application, and Spark is going to automatically take those and ship them to all the worker nodes so they can find your code. Okay. If you do this in Java, it's very similar. You have to use Java Spark context instead of Spark context to get a slightly more Java-friendly API. And you pass it, basically an array of strings for the jars. And if you use it in Python, you import PySpark.Spark context. And instead of passing jar files, you can pass a list of Python files for your code, or zip files, or Python eggs if you package your application into an egg. So that's all you do. And pretty much from there, you start using it the same way I showed before. So just to put it in context, here's the word count application I showed now with all the wrapper stuff around it to make it a standalone Python program. And really, it's just these couple of lines over here that say, OK, let's initialize a Spark context. And then we load our text file, and we do our word count stuff. And you can just run this on your cluster. OK. So to give you an example of a standalone app, I want to go quickly through one common application that's going to put together all the different concepts we talked about so far. And this is going to be PageRank. So PageRank's a good example to use for a couple of reasons. One is that it's a more complex algorithm than the things you typically do with map reduce. PageRank, you can express it as map and reduce steps, but you're going to have to do multiple iterations to converge to a value. So this is exactly the kind of thing that Spark was optimized for, with the support for fast data sharing and for general operation graphs. It also benefits from Spark's in-memory caching. If you look at the execution of PageRank, there are different iterations that happen, but many of them share the same data. They have to go back and look at a graph of web pages and look at some information about them. OK. So if you're not familiar with PageRank, here's a very quick overview of how the algorithm works. So the basic idea of it is we have a bunch of things in a network, like pages on the web or friends on a social network, and we want to give them a rank or a score based on the links pointing to them. And the idea is things have a high score if either a lot of pages link to them, that means they're important, or if some high-rank page links to them. So for example, CNN.com is important because many people have links to CNN.com, but if there's an article on CNN and CNN is writing about, whatever, some less popular page like AmpCamp or something, and CNN puts a link to AmpCamp, that means AmpCamp is actually probably important too. So that's how PageRank works. So the algorithm is actually like a fairly simple algorithm. You start each page with an equal rank, and then you run these iterations that are going to update the rank and reflect the links pointing to them. So everyone starts with a rank of 1, and on each iteration, page P looks at its rank, splits it among all its neighbors, and sends a contribution of that value to each of its neighbors. And then after everyone receives their contributions, they update their rank using this formula. Basically, they take all the contributions they receive, and they keep a little bit extra just so you don't go to 0. OK, so here's how it looks. So this is going to be a little graph of pages. These are some links. So for example, this guy has 1 link coming in, 1 link going on. And they each start with a 1. So when we do our first iteration of PageRank, these are going to be the contributions sent. So just as an example, this guy over here has only 1 link going out. So he's going to send the 1 to this page at the top. This one here has 2 links going out, so he will send 0.5 to each one. This one here has 2 links out as well, so he'll send 0.5 to the top guy, 0.5 to the bottom guy. Now, once everyone receives these contributions, they update their rank using the formula, and you can see, for example, the ones here only got a half because the half was passed on to someone else, but this one at the top got links coming in from many sources, so his rank is now higher than 1. Next time you iterate, you look at the current ranks, you send again the contributions based on those, and everyone splits up, like this guy split the 0.58 in half, and you update again, and you get a new set of scores. And it turns out that if you repeat this process a bunch of times, like say 10, 15 times, you converge to this final state, which is stable, and that's actually the page rank of every page. And that actually reflects some property of the graph. OK, so that's what it is. So I'll just show what this looks like in Scala really quickly. It's a fairly simple thing when you actually write the code in Spark, and it uses a bunch of the things we used before. So basically, we have 2 RDDs here. We have the links and ranks, and they're each going to be key value pairs. So the URL is the key, and for the links, we have a list of neighbors. For the ranks, we have the current rank. Okay, and then we have a bunch of iterations, and on each iteration we do a join, and the join is going to bring together the neighbors and the rank for each URL. So to send out our contributions, we need to know who our neighbors are and also what our current rank is. That's why we have to use join. And then we use flat map. So flat map was because we need to create multiple contributions. So we got in a URL and a links and a rank, and we're going to send out for each link. We're going to send out a tuple, which the key is the destination URL, and the value is we split up our rank by the number of links. So that's the formula I showed before. And finally, we add up the contributions by key using this reduce, and we map the values using the formula to actually get the new ranks. And that's what we do. We just run a bunch of these iterations, and at the end, maybe we want to save the output to a file. So that's what it looks like. I'll also show you real quick what the actual Scala code is like. Let's see. Actually, and maybe I'll just skip that because I want to have a bit more time for questions. But you can find the code in our examples anyway. Yeah, and then when you run this thing, because of the execution engine and because of caching, if you actually cache the links data set in memory, you can have it run actually quite a bit faster than a traditional MapReduce. So these are some results here for the code I showed before. So this is the cool thing. You write it in pretty little code. It's very easy to combine these steps, and it can also run faster. The same thing happens for other types of iterative algorithms. Later in the workshop, you'll hear a lot about machine learning, and these are some examples of machine learning algorithms that go faster with Spark. All right. So to conclude, I just want to say, how you could get started. You can get Spark on the project website. There are a whole bunch of documentation resources there, including 4 video tutorials on setting it up, which are really great to follow through. And there are several ways to run it. You can run it locally on your laptop using just Java, and it's very easy to launch on EC2 or on a private cluster. Let's see. That's pretty much it. So just to conclude, Spark is giving you a rich API for data analytics. It's meant to make it fast, both fast to write applications and fast to actually run them. We've seen real applications get 100x speedups. Of course, depends on the application, but it can actually really make a difference to them. And we have a growing community of people contributing, and we're very welcome to new people helping out as well. So that's it. Thanks. Yeah. Any questions? Yeah, go ahead.
When using Spark on Mesos, can it deploy the Spark itself, or it has to be installed on every?
Oh, yeah, good question. So when using Spark on Mesos, can it deploy itself, or do you have to install it beforehand? So Ben actually wrote a patch so you can deploy. You don't have to install Spark on each machine before. You just pass a jar file that contains all of Spark, and it will run.
So that third argument to Spark context, that's the local node Spark installation.
Yeah, it becomes a little.
Repeat it.
The third argument to Spark context, yeah, so it becomes, in that case, it actually doesn't use that argument, the Spark home. It just sends the jar as a whole. Yeah, you configure it in a slightly different way. But yeah, we're trying to make it, yeah, exactly, so you can deploy it this way. Yep. Go ahead, yeah.
In your Scala examples, I saw a lot of map and flat map and so forth, and you have filter. Do you implement filter with, and can you use RDDs in 4 comprehensions?
Can you use RDDs in 4 comprehensions? That's a good question. I think last time I checked, you actually could use them in 4 comprehensions. So 4 comprehensions, if you're not familiar, they're Scala syntax that looks, in a way, it's similar to like Python's list generators and things like that. It's a way to chain together maps and filters into into something that looks like a for loop. And I think, as far as I know, it does. So I don't know. I think we have a filter with, although it may not be exactly the thing that it should do for this. But I think it might be. But certainly, simple 4 comprehensions do work. Yeah. Yeah. Other questions? Yeah.
I was wondering, for the example on Spark context, we're using the term driver for the application that start Spark and RDDs, and there's a master URL, the term of master URL. So if you use cluster management, master URL will be directly to, like, it won't be directly talk to Yarn or Mesos, right? Is it like some listener from?
Yeah, so the questions about the cluster URL. So the cluster URL depends on the cluster manager you use. So the ones I showed were for Spark standalone cluster manager. That's this guy here I was showing before. It's this little interface here. So it's a very simple thing you can launch on each node. If you wanted to use Yarn, you would pass in a special URL for Yarn instead. And same thing for Mesos. And so that tells it what kind of cluster to connect to.
So you mentioned that for Python, you're pickling essentially the functions.
Yeah.
And you're using CPython. So
yeah.
does Spark support the C extensions like NumPy or SciPy or
Yeah,
PyCUDA?
yeah, great question. Yeah, so it actually does. So we use an unmodified Python. All we're doing is talking to it through like pipes and sometimes TCP sockets. And you can use NumPy in it. You can use any C library. Actually, it works with IPython as well if you like using that. You can find a bunch of our example programs for Python use these libraries. Yeah.
I have two questions. One is, have you brought this on top of like GPUs with the multi-core systems? And two, I was at the ParLab talk last week, and they did discuss PageRank, and it was essentially matrix operations. I wanted to know how good Spark was with matrix operations.
Yeah, good questions, yeah. So in terms of GPUs and multi-core, when your machine has multiple cores, we do use all of them, and the code is designed to be multi-core friendly as much as possible. So it actually scales pretty well to multi-cores. We don't do anything with GPUs yet. If you want, you could call into CUDA from inside your tasks if you wanted, and use GPUs. In terms of matrix operations, so it depends a lot on the type of operation. So PageRank is essentially on sparse matrices, and in that case, the way we're doing it here is essentially basically a distributed matrix multiply, and it works pretty well. If you're doing dense linear algebra, you probably want to use a faster library on each machine, like the Intel math library or things like that, and you can call into those from Java. So some of the machine learning stuff you'll see later actually uses native BLAS for those. Yeah. Okay, maybe. Yeah.
If your text is compressed, and when you do a map function, can it stay compressed until it gets to the nodes, or?
Oh, if your text is compressed. So compression is only when we have to store it. So when you store the data in HDFS or even in our cache, you can compress it. But the map function only sees the uncompressed version and only works on that. We do use compression for all our communication, and also if you want, you can cache data in compressed form. Yeah.
3 more questions.
All right, we can do, yeah.
Is there a single Spark process per node, or are there like separate processes for different pieces of work?
Yeah, so by default, we have only one process per node. If you want, you can launch multiple, like if your node is really big and you don't want just one giant JVM. But we use one because it's more efficient. You only load stuff once, essentially, and you can share data between the cores.
With respect to the closure mishaps problem, is there any chance of inferring what lexical state you want to drag across, or do you have to?
Yeah, good question. Yeah, so in Scala 2.10, using Scala macros, it's actually possible to infer that. So I think in future versions of Spark, we'll deal with that automatically, or at least we'll warn you at compile time if we can't deal with it. It might be possible in Python too. I'd have to look into it, but it's so dynamic that it might be possible. Yeah. Okay.
Hi, Matei. Question about shuffle. So what are the constraints in terms of shuffle performance, and what has happened over the last 1 year in terms of improving that? And where do you see this going?
Yeah, in terms of shuffle. So shuffle is actually one of the main things we're receiving contributions on, and the shuffle performance now is actually pretty decent, at least in most things we tried comparing to things like Hadoop or Impala. But we also have some pretty cool patches coming in from Yahoo and Intel that really improve it. So one of the things with that is, so we actually, even in the newest Spark code, it includes shuffle patches from Yahoo that make it scale better to multiple cores. And in the future, we're going to have patches that basically reduce the number of shuffle files and also compress the data in a somewhat smarter way. So you'll see a bunch of these. Actually, you can see the patches pending on the GitHub page for Spark if you want to look into them. What's the long-term constraint for shuffle? I mean, ultimately, so basically, in shuffle, all you have to do is send data as fast as the network, which usually is quite a bit slower than the speed of processing on one machine. So I think we'll pretty soon reach a very efficient shuffle for most networks in use today. But it is actually the main thing that affects performance in many jobs. So we're working pretty hard on it.
All right, thanks again, Matei.